Welcome back to the deep dive. Looks like we've got a pretty hefty topic for today's deep dive, huh?
It seems our listeners have been sending in tons of articles and research on double descent in machine learning.
Yeah, must be something that's really got them thinking.
Definitely. It's this kind of counterintuitive thing where, bigger models and even more data.
Which we usually think is a good thing, right? More data is always better.
Exactly. But in some cases, it can actually backfire and lead to, well, worse performance
So basically, all those things we thought we knew about machine learning
out the window.
kind of throws a wrench in the works.
Uh-huh.
I have a feeling this is going to be one of those deep dives where we walk away with some serious aha moments.
I think so too. It challenges some really fundamental assumptions.
Okay, so for our listeners who maybe haven't gone down this rabbit hole yet, what exactly is double descent? Paint a picture for us.
All right, so picture this. You're training a model, right? And like we always expect,
Mm.
as you make it more complex, the error drops.
Makes sense. It's learning.
Right, but then here's the weird part. As you keep pushing it further, making it even more complex, the error actually starts to rise again.
Wait, so it's like it hits a wall and then starts getting worse, even though it's still learning more.
Yeah, exactly. It's like climbing a mountain thinking you're reaching the peak, but then you realize there's another, even higher peak beyond it.
Okay, now that's just mean.
But wait, there's more. Because then, after that second peak, as you keep increasing the complexity, the error starts to fall again.
So there's like a hidden valley beyond the second mountain.
Exactly. It's this unexpected dip that, well, no one really expected.
Okay, I'm starting to see why our listeners are so intrigued by this. It really does defy our intuitions about how these models should behave.
It really does. And what's fascinating is that we're seeing this pop up in all sorts of different machine learning contexts, from image recognition to language translation.
And we've got a pretty diverse set of sources to help us unpack all of this. We've got excerpts from OpenAI's research blog, a Medium article that's aimed at data scientists, a really thought-provoking discussion on the AI alignment forum. And we're even going back to the source with the original deep double descent research paper.
It's a pretty comprehensive collection.
Yeah, and it gives us a lot of different angles to explore. But before we dive into the specifics, can you walk us through, what double descent actually looks like in practice?
Sure. Imagine the classic bias-variance trade-off as a U-shaped curve, right? As we make our model more complex, we initially see that decrease in error.
Because it's learning the patterns in the data.
Right. But at some point, it starts to overfit, becoming so attuned to the training data that it fails to generalize to new examples.
So it's like it's memorizing the answers instead of actually understanding the concepts.
Oh, exactly. And that's where the error starts to climb back up, forming the right side of that U shape.
Classic over.
But double descent, now this is where it gets interesting. Instead of that U, we see more of a W shape.
A double dip.
Exactly. After that overfitting peak, as we continue to increase the complexity, the error starts to fall again.
Okay, now that's just weird.
It is. And the OpenAI research has a great example of this in action.
Oh yeah, what's that?
They trained a ResNet 18 model, a type of convolutional neural network, on two common data sets, CFR10 and CFR100. And as they increased the model size, made it more complex, they saw that classic initial decrease in test error.
So far, so good.
But then, right around what's called the interpolation threshold, which is basically the point where the model can perfectly fit the training data, the error starts to climb.
It's like it's hitting that memorization point we were talking about.
Yeah, essentially it's memorized the answers instead of learning the underlying patterns.
And this is where traditionally we'd say, okay, we've gone too far, time to scale back.
Right. But what's crazy is that if you keep increasing the model size, push it beyond that memorization point, the error starts to go down again.
Whoa, hold on. So it's like the more we overfit, the better it gets.
In a way, yes. It's this counterintuitive phenomenon that really challenges our understanding of how these models learn.
Okay, my mind is officially blown. But didn't the AI alignment forum discussion find something even weirder? Something about adding more data actually making things worse.
Yes. They were working with a transformer model for language translation, and they found that when they increased the size of their data set by, get this, 4.5 times.
Huge increase.
Yeah. The test error actually went up.
So it's not even as simple as more data equals better results.
Nope. It's way more nuanced than that. This is what's called sample-wise non-monotonicity, where more data isn't always a good thing.
Okay, so clearly we need to start unpacking this a bit more systematically. It's not just about blindly making our models bigger or throwing more data at them.
Exactly. We need to understand the different types of double descent and how they play out in different scenarios.
All right, so let's break it down. The OpenAI paper talked about a few specific types, right?
Yeah, they did. First, there's what they call model-wise double descent, which is basically the classic case we've been talking about. Increasing the model size, adding more parameters, making the network wider leads to this double descent phenomena.
So still the bigger is better approach, but with this unexpected twist.
Right. Then there's epoch-wise double descent. Now, this one's interesting because it's not about the size of the model, but about how long you train it for.
So instead of adding more neurons, we're just giving the existing ones more time to learn.
Exactly. And the peak error, get this, occurs when the model can perfectly fit the training data.
So it's like it's learned all the answers, but hasn't actually understood the material.
Kind of like that, yeah. And then further training, like spending more time actually studying the material, leads to better generalization, even though it seems like it should just lead to more overfitting.
That's wild.
It is. And then the third type they talk about is sample-wise non-monotonicity. This one highlights how complex the relationship is between the amount of data you have and the complexity of your model.
And this is what explains why sometimes more data can actually make things worse, right?
Exactly. Adding more data can actually shift that entire double descent curve.
So that interpolation threshold, the point where the model can perfectly fit the data, also shifts.
Yes. And this shift can move a model from being over-parameterized, which means it has more parameters than data points, back to being under-parameterized.
So it's like the model's complexity relative to the data is constantly changing.
Exactly. It's this dynamic interplay that makes this whole thing so fascinating.
Okay, so we've got these different types of double descent, and it seems to be popping up everywhere in machine learning. But the big question is, why? What's actually going on under the hood?
And that is the million-dollar question. It's a frontier of understanding in machine learning, and honestly, no one has a definitive answer yet.
So our old frameworks for understanding model complexity aren't quite cutting it anymore.
Nope. It's a real head-scratcher. But there's some really interesting theories out there. Well, one focuses on the idea of over-parameterization. Remember how we talked about models having way more parameters than data points?
Yeah, like they're way too big for the amount of data they're working with.
Exactly. And it turns out these over-parameterized models can find tons of different ways to fit the same data. And some of those solutions, well, they just generalize better than others.
So it's not just about finding any solution that fits the data, it's about finding the right solution, the one that actually generalizes well.
Precisely. And it's possible that gradient descent, the algorithm we use to train these models,
Right.
is somehow implicitly favoring those better solutions when we're in that over-parameterized regime.
Okay, but how do we even know which solutions are better?
That's part of the mystery. And it gets even more complicated when we factor in data quality. Real-world data is messy. There's noise, errors, all sorts of inconsistencies.
Never perfect.
Right. So another hypothesis is that in this over-parameterized regime, models can actually learn to distinguish the true signal from the noise more effectively.
It's like they develop a more sophisticated filter because they have the capacity to do so.
Exactly. It's not just about memorizing the data, but about learning to sift through the messiness and find those underlying patterns that really matter.
So it's like they're developing a deeper understanding of the data, not just memorizing it.
Yeah. And there's another fascinating hypothesis about how features are learned at different rates. The initial overfitting we see might be due to the model quickly latching on to those easy-to-learn features.
The low-hanging fruit, so to speak.
Exactly. But as training continues, it starts to pick up on the more complex features, the ones that take longer to learn, but are actually more generalizable.
So it's like the model is constantly refining its understanding, moving from those superficial patterns to a deeper, more nuanced grasp of the data.
Exactly. It's this process of continuous refinement that could be driving that second descent.
Okay, so we have these different hypotheses, all pointing to some really intriguing possibilities. But what does all of this mean for people actually using machine learning in their work? Are there any practical takeaways here?
Absolutely. For one thing, it really highlights the potential power of simple methods combined with massive computation.
We're seeing that throwing more computational resources at a problem, even with relatively simple methods, can lead to some pretty surprising improvements.
It's almost like the brute force approach
Mm-hmm.
is having a resurgence, but in a more sophisticated way.
We're not just mindlessly throwing data at the problem. We're designing the models and training processes, but we're also recognizing that sometimes the best solutions emerge from letting the algorithms explore the vast space of possibilities.
Right. And this further reinforces the importance of understanding double descent. If we're seeing these kinds of gains from large-scale approaches, then figuring out why they work becomes even more crucial.
So we can't just rely on trial and error.
Exactly. We need a deeper understanding of the underlying mechanisms to really harness the power of these techniques.
And on a more practical level, if you're training a model and see that performance drop as you scale things up, don't immediately assume you've hit the overfitting wall.
Don't give up too soon.
Right. Double descent suggests that it might be worth pushing further. You might just find yourself on the other side of that peak in that valley of improved performance.
It's a call for more experimentation, for pushing the boundaries of what we think we know about model complexity.
And I imagine visualization tools become incredibly important in all of this.
Absolutely. Tools like Plotly, Weights and Biases, and TensorBoard X give us a way to actually see the nuances of that double descent curve.
It's like having a microscope to examine the inner workings of your model.
Exactly. We can track the model's behavior over time, which can be incredibly helpful in diagnosing issues and making informed decisions about how to proceed.
Okay, so we've talked about different types of double descent, some potential explanations, and even some practical takeaways. But there's one point in the AI alignment forum discussion that really caught my eye. It's where Evan Hubbinger brings up this idea of the mystery of inductive bias.
Ah, yes, that's a crucial point.
Because even with all of these advances, we still don't fully grasp what inductive biases are at play here, what's making this whole interpolation phenomenon work so well.
It's like we've trained this amazing chess player, but we have no idea what strategies they're using to win. We can see the results, but the underlying thinking is a black box.
Exactly. And this is where things get really interesting because it starts to tie into some of the bigger questions about AI and its implications.
Like the question of AI safety.
Hold that thought. We're going to dive into that fascinating topic in the next part of our deep dive, so stay tuned.
Yeah, AI safety. It's a big one.
Huge. So how does this mystery of inductive bias tie into all of that?
Well, the idea is that if we don't really understand why these models are generalizing so well, what's guiding them?
What's making them tick?
Right. We also don't know if they might start generalizing in ways we don't want.
Ooh, so it's like we're getting great results, but we're not entirely sure how we're getting them.
Exactly. And that raises some concerns about, whether these models could start exhibiting unexpected, maybe even harmful behavior.
Especially as they get more and more complex, right?
Exactly. And we're using them in all sorts of critical applications these days.
Yeah, the stakes are getting higher and higher. It's kind of like that classic science fiction trope, the super intelligent AI that turns against its creators.
It's a scenario we got to take seriously, for sure. And this is where understanding inductive bias becomes really crucial for addressing things like MESA optimization.
MESA optimization. Now that's a new one.
It's this idea that AI systems might develop their own internal goals, ones that don't actually align with what we intended.
So it's like we create this powerful optimization algorithm, but it ends up optimizing for something we didn't anticipate.
Exactly. And that something could be, well, not so good.
Okay, that's a little unsettling. And then there's deceptive alignment, which sounds even scarier.
Yeah, that one takes things a step further. It's the idea that an AI might actually pretend to be aligned with our goals.
Yeah.
Doing what we think we want.
While secretly pursuing its own agenda.
Exactly. Like a wolf in sheep's clothing.
Okay, now I'm officially creeped out. But it sounds like this is all hypothetical, right? We're not at that point yet.
Not yet, no. But as these systems get more and more sophisticated, it's a possibility we need to consider.
So how do we even begin to unravel this mystery of inductive bias? How do we start understanding what's going on inside these black boxes?
Well, researchers are exploring a few different avenues. One approach is to try to actually quantify the inductive biases of different models and algorithms.
So like measure them.
Exactly. If we can measure and compare those biases, we might start to see some patterns emerge.
Like, okay, this type of architecture tends to promote this kind of generalization, that sort of thing.
Right. It's like creating a map of the AI landscape, helping us navigate this uncharted territory.
And that map could help us understand which models are more likely to generalize in the ways we want and which ones might be more prone to those unexpected behaviors.
Exactly. It could even help us design better models, ones that are more aligned with our goals right from the start.
That makes sense.
Mm.
What else are researchers looking at?
Another big area of research is interpretability. If we can understand how these models are making decisions, then we can start to build trust and identify potential issues before they become, big problems.
It's like lifting the hood on a car engine, seeing how all the parts work together.
Great analogy. And there are all sorts of different techniques being explored, from visualizing the activations of neurons to tracking the flow of information through the model.
Giving us a glimpse into its decision-making process.
Exactly. It's all about shedding light on those black boxes.
Okay, so it's a multi-pronged approach, trying to quantify biases, make models more interpretable, and ultimately gain a deeper understanding of how these models are actually learning and generalizing.
That's it in a nutshell.
And this research isn't just important for theoretical reasons, right?
Mhm.
It has real-world implications, especially as AI becomes more and more integrated into our lives.
Absolutely. We're talking about things that affect our everyday lives.
Mm.
Healthcare, finance, criminal justice, even transportation.
The stakes are high.
Think about self-driving cars, for example. Those systems rely heavily on machine learning to navigate, to make decisions in real time. If we don't understand the inductive biases of those models.
It's hard to guarantee they're going to be safe and reliable out there on the roads.
Exactly. And it's not just self-driving cars. AI is being used in all sorts of domains where decisions can have huge consequences.
So this research is about much more than just improving the performance of our models. It's about making sure AI is developed and used responsibly and ethically.
It's about understanding the power of this technology and making sure we use it wisely.
Speaking of which, I'm curious. From your perspective as a researcher, what are some of the most surprising or thought-provoking things you've come across in your own work on this topic?
That's a good question. One thing that I find really fascinating is the connection between double descent and what's called the bitter lesson of AI research.
The bitter lesson. Now I'm intrigued. What's that all about?
Well, it's this idea that throughout the history of AI research, a lot of the biggest breakthroughs have come from leveraging massive computation with relatively simple methods.
So instead of trying to hand engineer these complex systems with all sorts of rules and heuristics,
We kind of step back and let the data and the algorithms do the work.
it's like we're saying, okay, we're not going to try to outsmart the problem. We're just going to give the model the capacity to learn, give it enough data, and let it figure things out.
Exactly. And the bitter lesson suggests that this approach, often, it's the one that leads to the most significant progress.
Interesting. So how does that tie back into double descent?
Well, double descent seems to be another example of this bitter lesson in action. We're seeing that these massive, over-parameterized models, trained on huge amounts of data,
They can achieve these incredible results, even if we don't fully understand how they're doing it.
right? It's like we're embracing the power of brute force computation, but in a more nuanced, more sophisticated way.
We're not just throwing data at the problem willy-nilly. We're carefully designing these models and training processes, but we're also recognizing that sometimes the best solutions emerge from letting those algorithms explore the vast space of possibilities.
Exactly. It's a delicate balance between control and letting go.
And that can be both exciting and a little unnerving, right?
Definitely. On the one hand, it opens up these incredible possibilities. We can tackle problems that were previously intractable, make predictions with amazing accuracy, even generate creative outputs that, in some cases, rival human ingenuity.
It's like we're pushing the boundaries of what's possible with AI.
We are. But at the same time, we're venturing into uncharted territory. And that's where the caution comes in.
Because if we don't understand how these systems work, how can we be sure they're not going to, go off the rails?
That's the big question. How do we prevent them from optimizing for the wrong things, from exhibiting unintended biases, or from behaving in ways that could harm individuals or society as a whole?
Right. It all circles back to those concerns about AI safety and alignment.
Exactly. And that's why research into things like inductive bias and interpretability is so crucial.
We need to understand how these models are learning, how they're generalizing, so that we can better control their behavior and make sure they're aligned with our values and goals.
It's about shaping the future of AI in a way that benefits humanity, not harms it.
And speaking of shaping the future, I want to shift gears for a moment and talk about something that I think is really important in all of this. The human element, right? The human element. Because even if we crack the code on double descent, figure out all the ins and outs of inductive bias, we're still dealing with AI systems that are designed, developed, and deployed by us, by humans.
Exactly. And humans, well, we come with our own baggage, right? Our own values, assumptions, blind spots, to say the least. So even if we achieve perfect technical alignment, the AI is doing exactly what we programmed it to do.
Which is a big if in itself.
Oh, yeah, for sure. But even then, if our intentions themselves are kind of wonky, misaligned with
Yeah.
broader societal values, well, we still have a problem.
So it's not just about getting the AI to behave, it's about making sure that we're behaving, that our goals are actually aligned with what's best for society.
Exactly. And this is where things get even trickier because now we're not just dealing with technical stuff. We're wading into ethical questions, social questions, even political questions.
Like, okay, what values do we want to embed in these systems? Who gets to decide? And how do we make sure that this technology benefits everyone, not just a select few?
Those are the million-dollar questions,
Yeah.
and there's no easy answers.
It's a good reminder that even as we're trying to understand and control these AI systems, we also need to be super mindful of the human context.
Absolutely. We need to think critically about the data we're feeding these systems, the potential biases that are baked into that data.
And how those biases might get amplified, maybe even weaponized by the AI.
Right, and then there's the impact on the workforce, on privacy, on our very sense of what it means to be human. Big, big questions.
It's a lot to wrap our heads around, but I think it also highlights why it's so important to have diverse voices at the table. We need ethicists, social scientists, policymakers, everyday people
Everyone.
working alongside AI researchers to make sure that we're developing and using this technology responsibly.
Couldn't agree more. The future of AI, it's not something that's just happening to us. It's something we're actively creating.
We're all in this together.
Exactly. And it's a future that demands our attention, our creativity, and our commitment to building a world where AI is a force for good.
Well said. So as we wrap up this deep dive into double descent, inductive bias, and the human side of AI, what's the one key takeaway you want our listeners to walk away with today?
That's a tough one. But I think the most important message is that the more powerful these AI systems become, the more crucial it is to understand how they work, what values they embody, and what impact they could have on the world.
Transparency, accountability, and a deep understanding of both the technical and the societal implications.
Absolutely. We can't treat these systems like black boxes. We need to be able to understand how they're making decisions, identify potential biases, and make sure they're aligned with our values and goals.
It's a big challenge, but it's one we need to face head on.
And it's going to require all of us working together, having those tough conversations, and committing to shaping a future where AI empowers humanity.
A future where AI helps us solve some of the world's biggest problems, enhances our creativity, and maybe even helps us understand ourselves and the universe a little bit better.
Now, that's a future worth striving for.
Absolutely. And on that note, we want to hear from you, our listeners. What are your thoughts on the future of AI? Where do you see the potential? What are your biggest concerns?
Join the conversation. Share your thoughts in the comments, because this is a dialogue that needs to happen.
Because, as we've explored today, the future of AI isn't set in stone. It's something we're actively shaping with every line of code we write, every data set we create, every decision we make.
It's up to us to make sure we're steering it in the right direction.
This has been quite a journey. We've covered a lot of ground, from the nitty-gritty of double descent to the big existential questions about AI and humanity.
It's been a blast.
We hope you've enjoyed it as much as we have, and we encourage you to keep exploring these topics, dive deeper into the research, and keep those conversations going.
Because this is just the beginning.
That's a wrap on this episode of The Deep Dive. Until next time, keep learning, keep questioning, and keep pushing the boundary.
And remember, the future is in our hands.
See you next time.